Hey everybody! Today we are going to continue our fantastical journey of DC circuits. What we've done so far is basically talked about situations in which you've got a battery and a wire and some sort of a resistor, and there might be a series of resistors, there might be resistors in parallel, but you can always break it down to where there's just essentially one resistor of equivalent resistance. And you know the rules from here. For each and every loop, the total voltage gained has to be the voltage dropped over the resistor. So if I've got a 12-volt battery, I would expect to drop 12 volts over the resistor. But by this point, you might have noticed some strange things happening. Let's say during the lab, if you measured the voltage across the resistor, you might have gotten a certain value, but if you measured it across the battery, that value might have been slightly bigger. Or, if during the simulation activity you hooked up a penny, which essentially has zero resistance, you might have noticed that as I drag the multimeter around, that voltage value is changing throughout the wire. So ultimately what that means is that, for both cases, I'm losing some voltage just to the wire itself. Well, the only way that voltage is going to drop over a wire is if the wire itself has some sort of resistance. And that's actually going to be true in real life, right? We're not going to have a perfect wire with absolutely zero resistance, unless we have some crazy superconductors for wires, which would be way, way, way too expensive. So, no. In reality, all wires have a little bit of resistance, and we can study this through what's called resistivity. Resistivity is basically just a proportionality between the resistance of a conductor, in this case a wire, and its various other properties, like the material that it's made out of, its length, and so on and so forth. So again, the properties include the length of the wire, the cross-sectional area, and the material that it is made out of. So we end up with this equation here. The resistance of a wire is going to be equal to the length of the wire divided by its cross-sectional area, all times this proportionality, and that's what resistivity is. It's denoted by the Greek letter rho, looks like a little p, a little squiggly p. And if the length is in units of meters, the cross-sectional area is in units of meters squared, and I've got ohms on the other side of the equation, the only way that'll work is if my resistivity is measured in ohms times meters, or ohm meters. Okay, so that's not too bad. But what is this idea of resistivity? What is this thing that's measured in ohm meters? What is this witchcraft, this demonry? Well, it really depends on what your wire is made of. Is it a copper wire? Is it a silver wire? Is it a lead wire? And so on and so forth. It depends on the material as well as the temperature, but we'll get there in just a second. If you go to page 879 of your textbook, which, again, here's a reminder, yes, you do have a textbook. It's located on the front main page of Canvas on physics. So go there, head to page 879, and you'll get a better version of this chart. It gives you a whole bunch of different types of materials and their resistivities at 20 degrees Celsius. Resistivity does change with temperature, but at 20 degrees Celsius, all these have a known resistivity in ohm meters. Now, the lower the resistivity, the more ideal the wire is. Right? Basically, the perfect wire would have no resistance, then all the voltage would be dropped over the various sources of resistance within the circuit. Since that's not the case, the best we can do is try to get as small of a resistance within the wire as possible, which is why wood is not a particularly good material to use for wires. It has a very, very high resistivity, which would cause a very, very high resistance in a wooden wire. So if we're dealing with problems at 20 degrees Celsius, then I can just hop to this chart. If I know the length of my wire, and I know the cross-sectional area of it, I can plug in the value from the chart on resistivity, and go from there and find the total resistance that I'm going to experience in that wire. Now, if we're not at 20 degrees, I got to take an additional step. The resistivity itself changes as the temperature changes. So the hotter the wire, the more resistivity it has. The more resistivity, the more resistance you're going to find in the wire. Generally, the resistivity is known at 20 degrees Celsius. That's around room temperature. So not only do these materials have a known resistivity, that's rho naught, that's what you're going to generally find from that chart on the earlier slide. So not only do they have a known resistivity at 20 degrees Celsius, depending on the material, they're going to have a different temperature coefficient. This temperature coefficient, called alpha, is actually measured in inverse degrees Celsius. When you multiply it by the change in temperature away from 20 degrees, the units will cancel, so inverse degrees Celsius cancels with degrees Celsius, and I get a new multiplicative factor to figure out my new resistivity at this new temperature. All right, so there's another chart that you will have to look at. This one is located on page 881 of your textbook. This gives you several different materials, as well as their temperature coefficients, again in inverse degrees Celsius. So, if you come across a problem where you need to find the resistance of a wire, but it's at, let's say, 50 degrees Celsius rather than 20, the first step would be to hop over to this temperature-dependent equation of resistivity, which again is rho, the new resistivity, equals rho naught, the resistivity at 20 degrees, times the quantity of 1 plus alpha, temperature coefficient, times delta T, the change from 20 degrees Celsius. So find your new resistivity, then take that value and plug it in to R equals rho times L over A, where again L is the length, A is the cross-sectional area. So a quick example of that. I like to flaunt my vast amounts of wealth because I'm a public school teacher, which means I'm just making bank all the time. So I only use pure gold wire for the electricity throughout my entire house. So if the wire heats up to 140 degrees Celsius, what is its resistivity? Well, to answer this, I'm going to have to go look at my chart real fast. And from the first chart, I will find the resistivity at 20 degrees of gold is 2.44 times 10 to the negative 8 ohm meters. And the temperature coefficient of gold is 3.4 times 10 to the negative third, inverse degrees Celsius. So to find the new resistivity, I would just use rho equals rho naught times 1 plus alpha times delta T. Since my new temperature is 140 degrees Celsius, delta T, that's the change from 20 degrees, that's just going to be 120 for delta T. So, plugging in that 120 for delta T, times 3.4 times 10 to the negative 3 for alpha, add that to 1, and multiply the whole thing by 2.44 times 10 to the negative 8 ohm meters, I should find a new resistivity of 3.44 times 10 to the negative 8 ohm meters. Cool. So, if I then knew a little bit more, if I knew the length of the wire, if I knew the diameter of that wire or the cross-sectional area, then I could just go in, plug in my new 3.44 times 10 to the negative 8 into rho times L over A, and find the total resistance, which is ultimately what matters for these wires. So a few tips to remember as you go through and solve these problems. All that wires are, they're just cylinders made out of some sort of conductive material. And a cylinder is, well, the cross-section of a cylinder is simply a circle, and the area of a circle is pi r squared. So when you solve for area, do pi r squared. And don't forget that a radius is also half of a diameter. A lot of times problems will just give you the diameter of the wire. You got to convert it to meters, divide it by 2, and square it, multiply it by pi before you actually find the area. Speaking of, don't forget to always convert back to base units. You're going to see a lot of millimeters and so on and so forth. So if you are uncomfortable with metric prefixes, which some of you may still be, practice, practice, practice that. And you're going to have to do a lot of conversions. Also, sometimes wire diameter is listed in terms of gauge. I'll be sure to give you the diameter, like basically just a certain gauge corresponds to a certain diameter of wire. Oddly enough, the higher the gauge, the thinner the wire. It's kind of reverse of what you would think. Really, the higher gauge just means higher resistance, so that means thinner wire. Right? So I think that is about it. Have some problems for you to work on, and good luck.